Welcome to ST30. There will be a longer introduction later, but since we are top of the schedule, we directly start with the first talk, which is assignment semantics for isorecursive types, session types given by Peter.
Thank you. Now someone should magically have the slides reappear.
Yes.
Well, anyway, so this is more like a cry for help, actually. So this is something that we started out. Janek is a student of mine. Vasco, well, I guess all of you know Vasco, and we looked at this and thought this is an interesting problem, maybe. I guess in this audience, I do not have to say the usual thing. A session type is something, so I'll just go straight into talking about session types with recursion. And what I just briefly would like to say, without getting technical, so the whole talk is really not technical, in any sort of real-world situation, I guess you need types with recursion to describe repeated communications, whether let it be finite or infinite. And in many papers, you actually have a very nice formal development. And then in the end it says, yeah, and if you want recursion, it's standard to extend it with that, and like with other stuff. And the real focus is usually on other features of the system that are going to be put forward. Nevertheless, recursion presents some quite interesting problems. And just as an example, I picked one which is like famous, namely duality for recursive session types. So that was a thing, where was that? In 2014, 2017 around, when Bernardi and Hennessy discovered that this nice, let's say naive definition of duality for session types is broken. So here you have the kind of obvious thing. So you have duality just flipping the direction of every communication. And then the naive extension to recursive types was, oh, well, if you want to take the dual of a recursive type, you just take the recursive type of the dual of the body. And for quite some time, this was accepted until Bernardi and Hennessy found, oh, this doesn't work out. Well, then, I think that's in their 2017 in the journal paper, they showed actually if you restrict the syntax, and this is what you can do, then it works out. And the restriction, and I'm telling you this because this is going to be the type syntax that I'll be talking about. What you can do is you just have to restrict the types that are transmitted in messages. You have to restrict them to be closed with respect to recursion variables. This is actually, it's not really a restriction because, as Bernardi and Hennessy showed, you can just unfold your recursive types until they meet restriction. But for now, actually, I'm not going to need duality in this talk. But just for now, I'm working with this subset, and I'm assuming this naive definition of duality. So. According to Bernardi and Hennessy, and actually we looked at it also in some detail, this is fine. Well, so that's just an example for an interesting problem in connection with duality. So the one that I'm actually going for is about like the nature of the recursion. So how you approach recursion in a type system. And actually there are two basic approaches that I guess most of you are familiar with. So on the one hand, there is equirecursion. And that's the idea that recursive types are just considered modulo unfolding. And this consideration, so this equation here is taken entirely silently. So whenever you need it, you just assume you're looking at the unfolding of the type, and whenever you need it differently, you can just fold it back. So they're considered equal. Some authors, I'm not sure, I don't see. I was thinking of Luca Padovani, but he isn't here. Some authors like to consider recursive types as the infinite unfolding. So your type is already an infinite object. The nice thing about that is you don't need any particular expression syntax. The downside is that if you're not careful, you need to do co-induction all the time, which is also tricky. Well, if you look at isorecursion, then it looks like things are much simpler in a sense, because instead of having this silent equivalence, you have you just consider the recursive type and its unfolding as isomorphic. Yeah? And you actually have to exercise this isomorphism in typing, so there is explicit syntax for introduction and elimination. And you find that also, I mean, this is standard stuff from textbooks. You'll find it in the Pierce book, in Harper's book, and wherever you look. And the oops. The interesting thing is, if you look at the literature on session types, you'll almost exclusively find them treated using equirecursion. So if you have recursion in session types, I was only able to find one or maybe two papers that kind of had a hint of using isorecursion at that point. All right. So here's an example why this is usually, well, why I think this is usually assumed. So the literature isn't really clear about it. So very rarely you find a half sentence that says something about it. Usually it's just tacitly assumed. Yeah, we'll add recursion and it's going to be equirecursion. So here there are two session types. Well, this is kind of sending integers ad infinitum, and this is sending one integer and then another integer and then iterating that. Well, and if you consider that modulo unfolding, then these two types are equivalent. And this is, I already said that, this is actually the common case in session type theories, which means a server that assumes S1, and forgive me for being fuzzy at that point. I don't want to put too much formalism in here. So a server assuming S1 can communicate with a client that assumes the dual of S2. There you have it. That's why I showed you the definition of dual in front. Yeah, so the server looks like this. It just sends and recurses, and that's it. The client just receives things. Well, for the sake of argument, it prints something. Yeah, but essentially these are two loops, and you can easily sync them. So the server needs to do 2 iterations, and the client has to do 1. And things are fine, because the only thing that's ever happening on the communication wire is this send and receive actions. Well, what does it look like in the isorecursive world? In that view, the two types are actually different. So there are two syntactically different, and also according to the isorecursion theory, there are different types, which means a server assuming S1 cannot communicate with a client assuming the dual of S2. That will not work, because, well, the server, the server obtains C in this recursive type. Well, on this recursive type, you cannot do any interesting action. You first have to explicitly unroll. So that's what's happening. Then you can do your action, and then you can recurse. Client, well, it has to unroll, then it can do 2 actions before it has to unroll again. Well, and the thing is that this unroll has to, well, at least that's the assumption in the literature, this unroll has to synchronize. And if you look at other uses of recursive types, that's how it usually works. So if you look at recursive types, isorecursive types in any other context, then you need this explicit roll and unroll thing. Now, so here the assumption is unroll is a synchronization operation. All right. However, well, the types look similar enough, and as equirecursive types, they are even equivalent. We can actually interpose some adapter process that kind of mediates between the types. And I'm just showing you one of them. I guess any one of you can construct that, and it just performs the rolls, actually the unrolls on the right side of the world. So you can see here, there's one unroll of C2, which is S2, which had the 2 communications before it recurses, and you see 2 unrolls of C1, which has this single, the tighter loop in a sense. And if you put this process between the sender that we saw on the previous slide and the receiver and the client, then they will be able to communicate via this adapter process. Now the question is, of course, how do we obtain this process? And it turns out this is reasonably fine. What you do is you formally write down the definition of equirecursive type equivalence, and that happens to be the same as a notion of compatibility between isorecursive session types, and that's going to be a co-inductive definition, usually. So, and I'm not going to show you the whole thing, just some key elements. Yeah, well, end is end, and if you are receiving something of type T, well, the types, the payload types, they have to be equivalent. At least their session type parts have to be equivalent. That's the definition of type equivalence here. And the continuation session also has to be equivalent. And the whole, well, problems in a sense come in with these unrolling rules. So if you find a mu on one side, then you are allowed to unroll that. And that's a nice co-inductive definition, and you can also show that it's productive and so on. So this defines a well-formed relation. And actually, already Simon, where's Simon? Simon and Hole in their paper on subtyping for session types. I mean, they essentially used, well, they didn't write it as a rule system, but this is in effect, well, they defined a subtyping relation. But if you ignore the subtyping, this is like the relation. If you tweak it into an equivalence, this is more or less the relation that you would get. Okay, well, now you have this relation. Now what we need is, oh, I already put it in the title, the adapter witnesses this type equivalence. So we'd better be able, if I have a proof, well, a proof structure for such an equivalence judgment, then I would like to be able to extract the witness, actually a process that mediates from one equivalent type to the other. Okay, so we can do that. That's also fine. Well, obviously, somehow this is a process that has to connect a channel of type end with a channel of the type of the dual of that, right? Because we want to interpose things. I don't really want to go. Well, anyway, so on one end you need to I don't even know which is which. So on one end you need to mediate a weight into a term. So one consumes the end question mark, and the other one produces an end blank, essentially. So here this is probably easier to explain. So on the left, right? So on the left we are receiving something of type T. Then here you have to interpose the equivalence of from T to U. That's like here, and then you send that out on the other channel, and there you go. That's like the implementation. And for the recursive parts, you just have to put the unroll operation on the right side. Now, wherever the recursion is, you have to do the unrolling. So that looks pretty cute, but unfortunately, it's unsatisfactory because if you look at the structures that you obtain from that definition, you will see that, well, you get infinite or circular witness terms. So that seems a bit unwieldy to work with. So you would, in order to work with that, you would have to come up with a theory to deal with these circular terms. So that doesn't seem so nice. But fortunately, since all the recursion is introduced with mu's, we actually have regular co-induction, which means that in such a proof tree, you only have finitely differently many subtrees, which means you can turn the whole thing into an inductive definition. And this is also, I think it's more or less standard, so you can find it in this paper by Gaffeyev, Levin, and Pierce, and in a newer one by Danino. So he spent quite a lot of work on that. So there's a standard transformation, which I'm not going into, but you can look at that in the paper. And then essentially you get an inductive definition of equivalence, and you also can construct witness terms that contain explicit recursion. And that's fairly easily. And termination of that process follows really from this fact that you've got regular co-induction. Right. That seems we're good now, right? So now what we can do is we can translate from equirecursion to isorecursion, and in order to do that, we somehow have to change this kind of silently unfold anything anywhere. We have to make that a bit more explicit. So in the type system, we put in an explicit conversion rule that, like known from other type system, and that's just there to apply the type equivalence. Yeah, so it's a non-syntax directed rule. You can put it anywhere in your typing derivation, and it's just there to put in your equivalences. Well, to put in your adapters, as you will see. Yeah, so you extend that namely to a translation, and the translation does more or less nothing except for the, well, it's homomorphic except for the places where you did have the conversion rule. For the conversion rule, you invoke the variant of type equivalence that also produces a witness term. Well, and you just interpose it, and you're fine. Yeah? So and it's also fairly easy to show that this translation is typing preservation. That's no witchcraft involved here. Also, you might wonder, can we come back? Well, you can come back also from an isorecursive system to an equirecursive system if you assume that the underlying isorecursive types are contractive. Usually, if you look at treatments of isorecursion, you don't assume that because there's always, well, the unfolding is explicit, so there's always something going on. But I guess it's for the application that we have in mind, it's good to assume that also isorecursive types are sort of contractive, because otherwise the whole bandwidth would be spent with unrolling and synchronization, and no information would ever be transmitted. So I think it's a reasonable assumption, and with that, the translation is actually just erasing the unroll statement, and there you go. Yeah, so the remaining thing, that's also a typing preserving translation, and you're good, apparently. Well, now we learned if I have a suitably nice, a contractive isorecursive program, can we actually make it talk to an equirecursive program just by erasing the unrolls, or just by making the unrolls silent? Yeah? So if the unroll doesn't do any communication, you kind of have the same effect. So that was actually the starting point of what we wanted to do. I can say a little bit about the reason. So to do that, we just have to ask that all the isorecursive types are actually contractive, right? So apparently then we can erase and go ahead. Well, I said that. Well, or can we? So what would this look like? No? I mean, if you want to do that, you would like to prove something, right? So you would like to prove that somehow the isorecursive version after erasing is still somehow in sync with the original. So okay, let's say we are translating from where to where? From equirecursive, I think that's the E, to isorecursive, and then here on the equirecursive side we take a step, and then we take the result, we translate that again, and then hopefully we can also reduce from the original one to the image, to the translation of the image under the reduction. I should have drawn a picture, but I'm sorry I ran out of time. Well, that would be nice if we could build up such a simulation, but no, it doesn't work. And essentially, what goes wrong? I have to go back to almost the first slide to show you what goes wrong. Like this one here. So there's a reduction that introduces this process here. Yeah. So in fact, this process is introduced wherever the translation introduces an adapter. Yeah. So every adapter at the type level looks like this. Yeah. So it actually has to introduce a fork, and a new channel, and then, well, of course, the body might look different, yeah, but essentially, this is what you have to do. Now, if you reduce that term, then the fork will go away. You have a separate process. The process will make some, a couple of steps, maybe, and then you're left with a different configuration where you have the original process, the adapter process, and maybe some client processes which are not really affected. Now, if the original system takes a step, well, you still, in the original system, you still have one process, right? Now, if you translate that, you get something with the fork, and you need to relate that to something that already has done the fork, where you have an extra process, and the extra process already did some steps. So clearly, it doesn't work to just assume we can continue from the translated term, because this fork is introduced everywhere. Okay. Right, so that doesn't work. Right, let's try to adapt to this situation. So somehow, since the translation reintroduces the fork, maybe we just went a little bit too far, right? So I should have. So there's nothing that I can draw on. So maybe we just went a little bit too far. No? So this was the original term. We made a step, and then. So we made the translation, sorry, then we made some steps down to here. Okay, now we make a step up here, we do the translation again. Maybe we can catch up with the term by just, well, here we have this fork stuff, and here we have the term that has the extra process. Maybe we can just get down there from this term. So that's kind of the idea of this situation. Unfortunately, that's also not working. So, and I would have considered that as some sort of administrative reduction, like in CPS translation. That there you actually, if you look at Plotkin's paper, there's a similar situation that the reduction is a little bit ahead of the translation, and you just can catch up using administrative reductions. But here, apparently, it doesn't work like that. So the current thing, maybe you need a simulation up to some equational theory, namely, if your source term makes an alpha step, then your translated term, well, it first does some equational steps, forward and backward, then it does the actual step that corresponds to the one in the source term, and then you have this equational steps again. So that seems to be the most promising. The only thing is, what usually is understood under equational theory is that you are able to apply the reductions in both ways. So first, I'm not really sure that anyone has looked at session type systems in that way, because it seems that you also have to play back, to do communicating reductions backwards in some places. And the second thing is, as far as we are currently into this problem, it seems you need equations that go beyond the mere reductions. So you need, it seems you need equations that have been shown by Benton and Kennedy and others. So they have been looking at equational theories for Moji's monadic meta-language. And they have some commuting equations where you can commute things that have disjoint effects. And if you have that, if you have these kinds of equations, I believe, or we believe, that you can get forward. But that's still up to be determined if these equations are actually applicable in this setting. So, well, so that's the current situation. So initially, I was, as usual, too optimistic, and it looked like it's an obvious thing, and you just do that. Well, typing, from the typing perspective, it is. But here, with proving this kind of correspondence, it seems we are hitting a brick wall, or we are trying to scramble up the brick wall. What would be nice to see after 30 years. That there was some sort of equational theory for session types, for functional session types. If anyone has spotted such a thing in literature, please let me know. I haven't I haven't really been able to find that. The other one was, so we discussed a lot also about bisimulation. I think bisimulation would help as far as to the second attempt, where, I mean, with this administrative reductions, where the original term is just a little bit ahead and you just need to catch up. I'm not sure if bisimulation would still help if you have to exercise this equational theory in a more non-trivial way. Well, yeah, that's it essentially. Thank you.
Thank you very much. We have time for questions.
Just about this last slide, you asked whether bisimulation could help. What about coupled simulation? You know that weaker notion of correspondence introduced by Thiemann and Thiemann.
Okay.
Concur paper which got the test of time award last year, and that's called.
I think coupled similarity was originally introduced by.
Right. No, sorry. No, that's a good point. Sorry. It was introduced by.
Yeah, but I was.
But it was used and.
But yeah, but I was thinking the same because it's exactly for something that is a little bit ahead of something else.
Mm-hmm, mm-hmm. Yeah, well.
So coupled similarity might be.
Yeah, I'm not familiar with it, but if you have a pointer for me, that would be great if we can find it.
Application in refinement, and it's really if you have something that is in between two bisimilar states, for instance, then you can use coupled similarity to get a meaningful equivalence there.
Yeah, we should talk about it. So.
I think you might also be able to use logical relations.
That's what I tried to set up. If you have any suggestion about that, actually, so I mean, you're doing logical relations. I know that, and there's some. Wasn't it by Jorge Perez even?
Sorry.
By Jorge, who is sitting behind you. So there's this paper with Frank and Bernardo, right? And it's so I looked at that, and it seems that worked because you are in this linear logic based settings where each process has a main channel as its objective, sort of, and then. I only looked at Jorge's paper actually, so far, and there it seemed to work because you could set up the logical relation around that channel, whereas here it's not clear in this functional term what is your focus.
Yeah.
So
I think it's not yet published, but we're working on a classical setting.
Okay, yeah. So if you have a good approach to do that. Yeah, that would be helpful.
I think what you can do with a logical relation, you can do this coupling because you can relate, like, you can relate different configurations.
Yeah. Yeah. So that was actually one of my first thoughts. Then I looked at their paper and I realized, okay, it works, or this approach works because you have this single channel that you can narrow down on, and you only have to, you can use the type of that channel to guide everything.
Right.
Yeah. So if you have a way of generalizing that, then help us.
You're hiring my co-author as a postdoc, so.
Okay, good. Yeah. Well. He wanted to do some other topic, but anyway, so he won't.
Yeah, so, thanks for the talk, Peter. So, actually, there are many interesting things. So, my first observation when you were presenting this was like these definitions of type isomorphism, in which you have, you want to equate two types, and then you find witnesses for two types, and then you make sure that the two types, witnesses are essentially equivalent to the unit or something like that. We did that also in conjunction with this logical relation. The logical relation was giving us the equational theory for that approach. So that could be one way to go. But also the idea of the logical relation that actually it's you can overcome one focus point, right? So there is this formulation of logical relation based on classical linear logic, also by Luis's student Pedro Rocha. So he had this way of proving like the usual stuff about like termination, confluence, so on, using logical relations in that context, and that was classical linear logic actually. So there is a different range of possibilities. I would say.
Okay. So there's light.
Yeah. Yes.
So thank you again.
Thank you.